Speech perception is the process by which the sounds of language are heard, interpreted, and understood. The process of perceiving speech begins at the level of the sound signal and the process of audition. After processing the initial auditory signal, speech sounds are further processed to extract acoustic cues and phonetic information. This speech information can then be used for higher-level language processes, such as word recognition. The range of the frequencies capable of being heard by humans is typically considered to between 20 Hz and 20,000 Hz. Frequencies higher than audible sound are referred to as ultrasonic, while frequencies below audible sound are referred to as infrasonic. Human is most sensitive to the sound with 3,000 to 5,000 Hz. There are three main components of human ear: the outer ear, the middle ear, and the inner ear. The outer ear includes the pinna, the visible part of the ear, as well as the ear canal, which terminates at the eardrum. The middle ear consists of a small air-filled chamber that is located middle to the eardrum. The inner ear consists of the cochlear, which is a spiral-shaped, fluid-filled tube. The sound information from the cochlear travels via the auditory nerve to the cochlear nucleus in the brainstem. The inner ear cochlear looks like a spectrum analyzer. The basal membrane is tonotopic so that each frequency has a characteristic place of resonance along it. Characteristic frequencies are high at the basal entrance to the cochlear and low at the apex. The sound perception of different frequency may not be a simple or linear relationship. Here is a short video to show the cochlear structure and working principle.
Let's start by taking a look at how the human hearing system works. The first part of the human hearing system is called the auditory periphery, which consists of the outer ear, middle ear, and inner ear. Sound waves in the air around us are captured by the outer ear, funnel down the auditory canal to the eardrum, which causes the three bones of the middle ear to push in and out on the cochlea. If we could unroll the cochlea, it would look like a long tube filled with water, with the basilar membrane running down the middle. The pushing by the last bone of the middle ear on the cochlea causes waves to travel down the length of the cochlea. These traveling waves in the cochlea are sensed by 3,000 inner hair cells arranged in a line down the basilar membrane, with the hair cells at the front of the cochlea picking up high frequencies, and hair cells at the end of the cochlea picking up low frequencies. Each hair cell has about 10 auditory nerve fibers, so the 3,000 hair cells convert their signals to spikes on the 30,000 fibers of the auditory nerve, creating a rich spectrotemporal representation of sound. Here are some examples of interesting sounds. Tones. Transients. Pitch. Ah. Formants. Ah-ee-ah-er. Speech. Audience voice processor. Music. Now that we're familiar with the computations done in the cochlea and the signal carried on the auditory nerve,
intensity of a sound is a physical quantity that can be measured and quantified. Acoustic intensity, I, is defined as the average flow of energy, power, through a unit area, measured in watts per square meter. Range of intensities is between 10 to the millimeters 12 power to 10 watts per square meter. This corresponds to the range from the threshold of hearing to the threshold of pain. Sound pressure is the local pressure deviation from the ambient atmospheric pressures caused by a sound wave. Sound pressure level SPL is a logarithmic measure of the effective pressure of a sound relative to a reference value. The sound pressure level of hearing threshold is defined as 0 dB measured at the frequency 1 kHz. For a quiet living room, the SPL is about 20 dB. For a busy street or noisy restaurant, the SPL is about 70 dB. On the airport runway, the SPL of the planes is about 120 dB. From the subjective hearing perception, pain begins to be felt above the level 130 dB. An absolute threshold of hearing is defined as the lowest level of a sound stimulus that the hearing organism could detect. The threshold of hearing is frequency dependent, and it can be expressed with the equation TF. The curve of the absolute threshold has been shown that the ear's sensitivity is best at frequencies between 1 kHz and 5 kHz, especially the range from 3 kHz to 5 kHz. Music signal has a larger range on frequency axis and SPL axis compared with speech signal. The level of a sound is expressed in units called phones, equal to the sound pressure level in decibels, relative to a pure 1000 Hz tone that is judged to be equally loud by listeners. An equal loudness counter is a measure of sound pressure, dBSL, over the frequency spectrum, for which a listener perceives a constant loudness when presented with pure steady tones. The same loudness levels can be arrived at by reference to equal loudness counters. Masking is the effect whereby some sounds are made less distinct or even inaudible by the presence of other sounds. We can make threshold measurements in presence of masking tone. The plots below show shift of threshold over non-masking thresholds as a function of the level of the tone masker. When the energy of tone masker is larger, the threshold shift is higher. Auditory masking occurs when the perception of one sound is affected by the presence of another sound. Auditory masking in the frequency domain is known as simultaneous masking. Frequency masking or spectrum masking. Auditory masking in time domain is known as temporal masking or non-simultaneous masking. As is shown in the figure, the sound below the threshold inquired is inaudible. When tone masker occurs, there will be a masking threshold. The signal below the threshold cannot be perceptible due to the presence of the tone masker. Temporal masking or non-simultaneous masking occurs when the sudden stimulus sound makes inaudible other sounds which are present immediately preceding or following the stimulus. Masking, which obscures a sound immediately preceding the masker, is called pre-masking, and masking, which obscures a sound immediately following the masker, is called post-masking. We can employ the masking principle in perceptual audio coding. Masking enables tones or noise to hide another tones or noise. This is the basis for perceptual coding. For example, MP3. As is shown in the figure, the bit allocation is set to be 0 if the power spectrum is below the predicted masking threshold. Redundancy can be removed relative to the masking threshold. Finally, bit assignments are different among different frequency bands. If two sounds of two different frequencies are played at the same time, two separate sounds can often be heard rather than a combination tone. The ability to hear frequencies separately is known as frequency resolution or frequency selectivity. When signals are perceived as a combination tone, they are said to reside in the same critical bandwidth. Critical bandwidth is measured as the bandwidth of masking noise beyond which further increase in bandwidth has little or no effect on the amount of masking of a pure tone at the center of the band. The noise spectrum is essentially rectangular, thus the notion of equivalent rectangular bandwidth, ERB. Critical band describes the frequency bandwidth of the auditory filter created by the cochlear, which is the sense organ of hearing within inner ear. Roughly, the critical band is the band of audio frequencies within which a second tone will interfere with the perception of the first tone by auditory masking. Critical bands are nonlinear, level-dependent, and the bandwidth decreases from high to low frequency. The human ear has higher frequency resolution in lower band. That's all for this session. See you next session.